So this is the Bellman algorithm, right? In the Bellman algorithm, you have n amount of vertices, right? Just like Dijkstra, you're going to create n minus 1 tables. So you have 6 vertices, so you're going to create n minus 1, which is 5, right? Now, to keep track of where you are in the Bellman, you need to use a counter, which is named k, right? And k goes from 1 to n minus 1. So k will go from 1 to 5 in this case, right? So I went ahead and dropped my tables already, right? Now, the first table where k is equal to 1, I already did it, right? So I'll just walk back through it. So for position 1, oh, by the way, the starting vertex in this case is 1. He must give you the starting vertex. So for this table, from 1, we could reach 1 in the table, and that will cost us 0, right? And the parent of 1 is nil, right? Now, the rest of the vertexes here, or the vertices here, we want to see if we could reach them directly from vertex 1. So, could we reach 2 from vertex 1? Yes, we can, at the cost of 2. So we update it here, and the parent here. Could we reach 3 from 1? Yes, we could, at the cost of 4. So we update it here and we update it here. Right? Could we reach 4 from position 1? 4 is here and 1 is here. We can't reach it directly, so we put infinity. Could we reach 5 from position 1? No, we can't. Infinity again. And the same thing for 6, right? Now that is the easiest table in the Bellman algorithm. That is the initialization table, right? Now when we reach where k is equal to 2, we need to keep going back to this table here to get what we want, right? So we want all values here that are not infinity, right? So that means we want 1, 2, and 3, right? This is important because when we follow all the values for the rest of these, we are going to be using 1, 2, and 3 to find the smallest values for each one of these columns here, right? So what I mean by that is, since we're doing 2, k is equal to 2, so k is equal to 2, so we're on table 2, and the values we want is 1, 2, 3. Alright, we're going to do column 1 first, right? So for column 1, you could put 1 like this somewhere on your paper, and you could say v1, v2, and v3, meaning this one here, this one here, this one here, that is not infinity, right? And it goes to reach 1 from vertex 1, we're leaving that out, right? We just put for that nil, right? It goes to reach 1 from vertex 2. We cannot reach 1 from vertex 2, so we put infinity, right? We cannot reach 1 from vertex 3 either, so we put infinity, right? So since the smallest value here is infinity, we're going to take back the one that we had from up here, which is 0, right? So 0 and nil, right? So now we want to do the same thing but for value 2, right? Draw back v1, v2, v3, right? So we want to see what is the cheapest to reach v2 from v1, v2, v3, right? So we go back to the table. To reach v2 from v1 is a cost of 2. So we come here and we update it here, right? Since we're doing 2, we're not going to do anything with this one here. So we're going to leave it as nil, just for now, right? To reach v2 from v3, we could reach v2 from v3, we cannot, so we put infinity, right? And we choose the smallest out of all of these. The smallest out of all of these is 2, right? So we update it here, and the parent is v1, right? So now we go to 3, right? So we have v1, v2, and v3 again, right? So we're going to see what is the cheapest to reach v3 from these 3 vertexes, right? So to reach 3 from v1 costs 4, right? To reach 3 from v2 will cost -3 plus what is the value of 2 here, which is 2, right? Which will give you -3 plus 2, negative 1, right? So to reach v3 from v2 will cost you negative 1, right? And because we are on v3, we're going to leave here blank, so we just put nil, right? Now we take the smallest values out of all of these here, which is negative 1, and we update it here, right? Now we update the parent, which is v2, right? So now we're going to do 4, right? Right, so could we reach v4 from v1? No, we can't, so we're going to put infinity. Could we reach v2 from, could we reach 4 from v2? Yes, we could reach 4 from v2 at the cost of 1 plus 2, which is 3, right? So we update 3 here. Could we reach v4 from v3? Yes, we can at the cost of negative 4 plus 4, right? So this is what we have to pay attention to when we're doing this. We could reach v4 from v3 at the cost of negative 4 plus the value of 3 in the previous table, right? The previous table, the value of 3 is 4 plus this negative 4 here, right? So that is 0, right? And we choose the smallest out of these 3, which is 0. So 0, and the parent is v3. Cool. So we're going to do 5 now, right? So v1, v2, v3. Same story again. Could we reach v5 from v1? No, so we put infinity. Could we reach v5 from v2? Yes, we can at the cost of 5 plus 2, 7, right? Could we reach v5 from v3? v5 from v3, yes, we can at the cost of negative 2 plus 4, which will give us 2. Right? So we choose the smallest, which is 2, and we're going to update the parent to 3. Right? So now we're going to do 6. Right? So could we reach 6 from v1? No, we can't, so we put infinity. Could we reach 6 from v2? No, we can't, infinity again. And we can't reach 6 from v3 either, so infinity, right? So in a case like this, 6 remains as it was in the previous table, infinity and nil, right? So k2 now is finished, right? And we have to do this 3 more times because it's 6. So we go to where k is equal to 3, right? And I'll make our next video with the rest.